Hello everyone, we are at the topic of diodes and we are studying the waveform shaping circuits using diodes. In today's lecture, we're going to look at a clipper circuit. In the previous video, we looked at a half-wave rectifier circuit using a diode, and this is the circuit that we looked at. And also we found the transfer function of this two-port network and found the output for a sample input signal, which was a triangular waveform. We calculated this output waveform that is shown in here. The clipper circuits, in terms of the structure or circuit configuration, are similar to the half-wave rectifier circuits, with the only difference that the output in a clipper circuit is taken from two ends of the diode. However, in a half-wave rectifier, the output is taken from two terminals of the load resistor. We are going to analyze the operation of clipper circuit and find its transfer function. Also, we're going to draw the output for a sample input signal. As you can see in this figure, this clipper circuit clips the input signal at a certain threshold value. In other words, this circuit doesn't allow the output to go beyond a certain threshold value. At that threshold value, the output is going to be a constant value, and the value of the output signal does not increase beyond that threshold value. We are ready to solve this clipper or limiter circuit and find the output versus input. Here are the KVL equations that I wrote for this circuit and the Ohm's law for the voltage across the resistor. So this is my VR and this is voltage across the diode. Using the KVL in the main loop, I have VI equals to VR plus VD. Also, I can write another KVL in here that tells me minus V out plus VD equals to 0, which tells me that V out is equal to VD. So also Ohm's law for the voltage across the resistor is provided here. Now I have one diode, so there are two possible states for the diode. Either the diode is either off or on. If the diode is off, the current through the diode is going to be equal to 0 in the piecewise linear model, of course, and the voltage across the diode is less than VD naught value. Since I have VI equals to VR plus VD and VD is equal to V out, I can write it as VR plus V out, and I'm going to write VR as R times ID plus V out. From there, VI is going to be equal to V out. ID is equal to 0. And I'm going to use this inequality to find the range of VI for which the diode is going to be off. Again, from the first KVL, I have VI equals to VR plus VD, and VR is equal to 0. From there, I have VI equals to VD, which is less than VD naught. From there, I get VI is less than VD naught. So for VI values less than VD naught, VI and V out are going to be equal. Now let's look at the case of diode being on. I know that when the diode is on, voltage across the diode is equal to VD naught and the current through the diode is positive. Because V out is equal to VD and that's equal to VD naught, I know the voltage at the output is going to be a constant value equal to VD naught. Now I'm going to use this inequality to find the range of VI for which this condition holds. I can write ID equals to, ID is the current that flows through the diode and the same current flows through the resistor. So this is ID as well. As a result, I can write ID equals to VI minus VD divided by R. This current is greater than or equal to 0. From there, I know that VI must be greater than or equal to VD, which in this case is equal to VD naught. So for VI greater than or equal to VD naught, V out is a constant value equals to VD naught. So we found the equations for our transfer function, and as you can see, the transfer function is nonlinear. Here is the graph for V out versus VI. And from this transfer function, what I see is that for VI values greater than a threshold value, which is VD naught for this circuit, the output is going to stay at a constant value and the value of the output signal is not going to go beyond this VD naught point. For VI values less than this threshold value, V out and VI are going to be equal. Let's solve an example of finding the output signal for the given input signal using the transfer function that we just calculated. The input signal in this example is a triangular waveform. I'm going to label the peak value of Vi as V peak, and this V peak is greater than VD0 volts. So this is again my V peak, and I'm looking for the time points at which the value or the amplitude of Vi is greater than VD0. So let me label VD0 volts here, and okay, so this in this time point the value of Vi is less than VD0. Again, from this time point to here the value of Vi is less than VD0, and again in this time point the value of Vi is less than VD0. Now I know from the transfer function that when Vi is greater than VD0 volts, the output is going to be a constant value equal to VD0. So in this time range, this is my output voltage. I'm plotting V out of t with red ink, and again in this time interval V out of t equals to a constant voltage value equal to VD0. And for other time intervals at which Vi is less than VD0 volts, V out and Vi are the same. So V out, I'm gonna draw the same line for Vi as the value as the graph for V out. V out and Vi are the same for Vi less than VD0. So this is the graph of V out of t. It is interesting to note that we can adjust the limiting voltage in the clipper circuit. In the previous example, the output was taken from two terminals of the diode. As a result, the output voltage was limited to VD0 volts and voltage levels below VD0 volts. If we want to change this threshold value, we can add a DC voltage source in series with the diode, as you can see in the below configuration. And in this configuration, when the diode is on, V out is going to be equal to VD0 plus VDC. I can write the KVL in here. This KVL is going to give me this equation. So when the diode is on, the output is going to be limited to VD0 volts plus voltage of this DC voltage source. So by changing the value of VDC, I can change the threshold value at the output. We can adjust this limiting voltage using a Zener diode instead of a DC voltage source. As you can see in this circuit configuration, when D1 is on and D2 is in the Zener region, the output is going to be limited to less than VD0 plus VZ value. So I'm gonna, if I label this one as VD and this one as VD1 and this one as VD2, when D1 is on and D2 is in Zener region, then VD1 is going to be equal to VD0 and VD2 is going to be equal to negative VZ. V out is going to be equal to VD1 minus VD2 using the KVL in this loop, and V out is going to be equal to VD0 plus VZ. So when the diode 1 is on and diode 2 is in the Zener region, V out is going to be equal to the Zener voltage plus VD0 volts. And the other possibility for the operation of these two diodes is that both of them are off, and if both of them are off, the current through the diodes, or which is the same current that flows through the resistor, is going to be equal to 0. From there, when both of the diodes are off, V out is going to be equal to Vi. If we flip the direction of the diode and in this connected in this configuration, V out is going to be limited to negative VD0 minus VZ volts. I can write the voltage across this diode as VD, and using this KVL I have V out equals to negative VD minus VDC. And when the diode is on, VD is equal to VD0, so V out is going to be equal to negative VD0 minus VDC. And the same goes here. I have VD2 plus minus, this is my VD1. When D1 is on and D2 is in the Zener region, the current flows in this direction in my circuit, and VD1 is going to be equal to VD0, and VD2 is going to be equal to negative V Zener, and V out is equal to negative VD0 minus VZ, which is the same as V out equals to negative VD1 plus VD2. Finally, we can see that it is possible to clip both the top portion and bottom portion of the signal simultaneously. This circuit configuration is going to allow me to cut the input signal from both the bottom portion and top portion, and by adjusting the values of DC voltage sources VDC1 and VDC2, I can adjust these threshold values. If you look at this figure, V out is going to be limited to less than VD0 plus VDC1 or greater than negative VD0 minus VDC2. We can use Zener diodes to simplify the top circuit. The below circuit, the bottom circuit, can operate just like the top one, and with this circuit, V out is going to be limited to less than VD0 plus VZ1 or greater than negative VD0 minus VZ2. I can label the voltages across the diodes as VD1 and this is VD2. So when diode 1 is in the Zener region, diode 2 is gonna be forward biased and it can conduct. One condition of operation of these two diodes is D1 being in Zener and D2 being on. The other case is when D2 is in the Zener region and D1 is forward biased and on. And the other condition is that both of these diodes are off. And for that case, V out is going to be equal to Vi. In summary, today we looked at clipper or limiter circuits. These are waveform shaping circuits using diodes. We looked at clipper circuits that would cut the top portion of the input signal, or cut the bottom portion of the input signal, or cut both top and bottom portions of Vi simultaneously. We also looked at the circuit configurations that are used to adjust the limiting voltage level in the clipper circuits. Thank you for watching.